Hello everyone, this is Luca from Ninja, and today we will present Whidboard, which is also known as the ultimate Swiss Army knife for hardware hackers out there. So first of all, before introducing Whidboard and all its features, let's overview the situation we are dealing when talking about IoT and IIoT or embedded devices security nowadays. So as you can see here from this slide, many cases happened already in public. Affecting vulnerabilities and incidents affecting IoT and embedded devices. For that reason, OWASP organization developed the top 10 IoT, which is the top 10 most common vulnerabilities related to IoT devices. And also for that reason, the OWASP organization developed also the IoT security verification standard, also known as ISVS, which aims to establish levels of confidence in the security of IoT ecosystems. You can see it as a sort of security checklist with different items divided per levels. Or granularity levels. And these items allows testers, security testers, hardware hackers to verify and confirm or deny that certain amount of vulnerabilities related to IoT embedded devices are present or not inside different targets or DUTs, device under tests. One common problem that is affecting many IoT and embedded devices nowadays is the fact that there are a lot of electronics legacy IoT embedded hardware features available nowadays in IoT devices. As you can see from these funny picture here, we can pretty be sure that many IoT embedded devices nowadays in production are still adopting vulnerable protocols like I2C and SPI protocols, which do not have any authentication, integrity, or encryption. So out there are plenty of potentially vulnerable devices. It's just a matter of how to deal with them, how to communicate with them, how to discover these kind of vulnerabilities. For this reason, a hardware hacker would need these kind of devices like logic analyzer, JTAG SWD debugger, UART to USB connector adapter, SPI I2C memory programmers, readers, and writers. For that reason, back in time, I started developing my own boards in a way that I could bring around one single board that would be able to deal with all of those protocols. So it started a few years ago with Focaccia board, then it evolved with Bertolino board, Nando board. Last year, a couple of years, I developed the Bruschetta board, and nowadays we arrive with the Whidboard board available. As you can see, the previous boards were shared on GitHub with, any other researcher out there, and plenty of them managed to build them and play with them. So it became kind of obvious that people out there need these kind of boards and multi-tools to deal with IoT devices, embedded devices, to hack them and test their security. So what is Whidboard in short? Well, as I mentioned before, it is the ultimate toolsuite for hardware hackers. It is composed of three major parts. The Bruschetta-Pro, that can be seen as a multi-protocol debugger, which allows you to deal with, communicate, and interact with different protocols, UART, SPI, I2C, JTAG, and SWD, at different logic levels as well. So with one single board debugger, you are allowed to deal with different devices that use different voltage levels, 1.8, 2.5, 3.3, and so on. It also allows you to deal with pin enumeration. So it's acting as a pin enumerator, has 24 channels to connect to 24 different pins or test pads, or test points on a target, and be able to figure out and enumerate the pins for UART, JTAG, SWD, and so on. And it also has a 8 channels logic analyzer feature. This allows you to sniff that data buses on some specific DUTs, device under test, and allows you to, reverse engineer some specific electronics related protocols. As we can see here a bit more in detail, The three major components or features of the Whidboard are the multi-voltage UART, JTAG SWD, I2C, and SPI protocol debugger. Here, we already have on it some specific sockets, deep 8 shape footprint sockets that allows you to use some specific adapters we will see in the next slides, and also all the other pins that allows you to interact with UART, protocol JTAG, or SWD. Then we have also the logic analyzer with 24 megahertz, 8 channels logic analyzer here. As you can see here, it's particularly nice because as I designed it, we have different ways to connect to those channels with strip pins, headers, female, male, and also screw down connectors in a way that instead of having DuPont wires to connect to them, you can just use, loose wires and screw them inside without, soldering or anything like that. As well as the third feature is the 24 channels multi-voltage pin enumerator, which it looks like it supports, we will see later, it supports the JTAG firmware. Is multi-voltage, so you can attach different targets on it, and allows you to enumerate different pins for different protocols like UART, SWD, and JTAG. Regarding the logic levels and voltage range, it supports different logic levels. You just need to switch the jumper on the PCB to switch from one logic level to another. Together with the Whidboard, you will find on the GitHub repo a new live Linux-based OS called WidOS, which embeds already pre-flashed and pre-built and pre-configured all the tools that are supported by Whidboard. So you will be able to find FlashROM, OpenOCD, Xander, UFProgs, PulseView, SIGROC, and so on and so forth, like the major utilities used for testing hardware from different point of views in the live OS itself. So you can download the ISO and then deploy your VM or install as a OS on your host PC. So let's look a bit deeper a bit about the Bruschetta-Pro, sorry. The Bruschetta-Pro is that multi-protocol, multi-level debugger that allows you to communicate with different protocols. So let's start with the UART. What is UART? UART is the acronym that stands for Universal Asynchronous Receiver and Transmitter. It's one of the most used device-to-device communication protocols. Is most likely the main starting point you have to deal when hacking hardware or embedded devices, IoT devices, IIoT devices. The trick here is that you need to connect the RX from one device to the TX of the other, and vice versa, the TX of the first device to the RX on the other. Of course, I will not go deep in details because we have a dedicated training for this on my website, wait.ninja. Here is just a quick introduction to give you an idea of how it looks like and what you can do with a UART console terminal. So what we can do with a UART console? Well, we can deal with the bootloader. So we can do bootloader live hacking, like bypassing root access, getting root access with some tricks like init bnsh, or dumping the firmware with md commands or other stuff. We can get a final shell into the fully booted device. This shell can be either limited or high privileged, like root shell directly. And with that, we can do different things: live analysis, live forensics. We can dump the firmware. We can extract the firmware through DD and netcat, TFTP, and so on and so forth. If there is a limited shell, we can try to brute force the password, or we can try to bypass some features as well. How to interact with the UART? Well, as I mentioned before, the live OS, WidOS live ISO is fully set up and configured to deal with all the features of Whidboard. However, you can use also Windows, for example. We'll see that all these features can be used and tools can be used also on Windows. In this case, interacting with a UART on a target is very simple. You just need to connect on Windows to a COM port. Once plug the USB cable into the Whidboard and pick the right baud rate that you will discover eventually with the Pin Enumerator. From Linux point of view, you can use simply screen utility, Linux utility, and connect to ACM1 and the right baud rate of the target. So as you can see here, this is a quick video of how it looks like UART interaction. This is our target. This is Whidboard. At the same time here, as POC, proof of concept, I connected both UART and the logic analyzer. In a way, I can show you from one side how is the interaction with the UART console with the target, and the other, in the meantime, we will sniff with the logic analyzer. So in this way, you get both features working and confirm that they are both working. So here we see the output of the target bootloader, the U-boot. And on this side, you see that the logic analyzer started sniffing the RX and TX channels. And on the TX, so transmitter channel, that is spitting out data from the DUT, from the device under test, we see clearly some, data coming out. And if we use the right dissector on pulse view, we can literally read what is spitting out. So this is exactly the same data that is spitted out on the UART console. So as you can see, both features are working pretty fine. If we look from SPI point of view, SPI is yet another protocol, very old, obsolete, but still used quite often in IoT devices. It stands for Serial Peripheral Interface, is one of the most widely used interfaces to communicate between microcontroller and peripherals of different kind. In our case, we are using it to read flash memories, SPI flash memories. So in this case, flash memories, SPI flash memory can have different footprints. Usually are, most commons are SOP8 or SOP16, but there are also, WSON8, for example, or even smaller, or even BGA's style. In this case, to deal with them, we have different compatible adapters with Whidboard. So here is some example. On GitHub, you will find even more example available. You can easily buy them on eBay, Amazon, AliExpress, and so on and so forth. So different footprints are supported by Whidboard itself. So easy to deal with this kind of board. These kind of flashes, memory flashes. From software point of view, we have three different softwares, Xnander, FlashROM, and UFprog. All of them are supported on both Windows. As you can see here, we have a couple of examples on Windows and also on Linux. So all of three are both working on Windows and Linux. On GitHub, you can find the precompiled version for Windows and also the ISO, WidOS Live ISO containing the precompiled version and pre-configured versions for Linux. So everything is set up. Here you have also the pinout for the clip. So as you will see in this video, we will use an external clip connected to it, which has attached the clip itself on the SPI flash memory on the target. Here we put this cable to put in reset the CPU in a way that we are able to just keep the CPU or the SOC system on chip silent, meanwhile dumping the firmware. And here what we do is we will use FlashRAM. Now we double check that in the VM the Whidboard is connected to it. And then we will use FlashRAM to read it. As you can see, pretty easy. It's reading the flash, done. And now what we will do is we will try to verify with Beamwalk if we manage to properly dump the firmware, and also we'll try to extract the firmware. So now let's try if Beamwalk works. As we can see, Beamwalk managed to figure out the content of the flash, so we found something in it. And now if we try to look with the binary, with the file manager inside the binary extracted file system, embedded file system directories, we can see that we can see all the files. So here, for example, password D, we can even open shadow. Let's see. So also shadow password. So pretty easy everything, I would say. So here now we can access even the SBin directory and look for interesting elves to decompile and reverse engineering with Ghidra, which we also have installed pre-configured on WidOS Live as well. Here another video. In this case, instead we will use an external SOP8 connector socket to dump the SPI flash directly from the chip. So imagine that you remove physically the chip from the PCB of the target with a soldering iron, hot air iron, and then you just plug it in on that socket and then use again FlashRAM to dump the firmware. So in this case, you can clearly see the commands used, again reading the flash. As you can see, it's pretty fast FlashRAM with Whidboard. And then we can try again with Beamwalk. And voila, we managed to extract it once again. So easy. I2C is yet another protocol. It stands for Inter-Integrated Circuit. It's a two-wire serial interface that is the third most common widely used protocol to communicate between microcontrollers and peripherals. Also, this protocol is supported fully by Bruschetta-Pro, which is part of Whidboard. It's very fast. We have a main tool is called Xnander, which is both available for Linux and Windows. And we have also the Whidboard's native Windows tool. If you want to play with it, is open source and is on the GitHub repo as well. It's pre-built and there are also sources available, so just feel free to try it out. Personally, I would recommend Xnander because it supports both SPIs and I2C memory. So it's quite powerful. As you can see here is an example of the dump. Pretty fast, pretty easy. Here, quick proof of concept. So in this case, this was a memory, I2C flash memory extracted from a target. Plugged on a socket, and there with Xnander, you just take a fraction of a second to dump it, and then you can just read it with any xdump, binwalk, or whatever. Of course, this one was a proof of concept, so I just used some strings. I wrote random stuff inside it just to prove that it's easy to read it and write it eventually if you need in the future to modify, tamper the firmware, and put it back. Easy peasy lemon squeezy. Next, JTAG. JTAG is yet another, not very commonly available nowadays because is so powerful having access to JTAG that manufacturer understood that it's too dangerous to leave it available. So most of the times you will have to use the pin enumerator to find the pins because they are hidden quite well. Sometimes it will be disabled, so you will have to use fault injection. But in the rule of thumb, JTAG, which stands for Joint Test Action Group, is an industry standard that allows you to do very low-level debugging of any kind of embedded hardware, IoT, IIoT device. For that reason, Bruschetta-Pro and Whidboard, of course, support JTAG. What you can do with that JTAG access, well, you can gather information about the hardware, so memory, processor, and so on and so forth. You can dump the RAM, so access sensitive data that usually are encrypted at rest. Instead, they are available in plain text in the RAM itself. You can do live debugging with new debugger, GDB. You can change the behavior of programs on runtime. You can even spawn reverse shells to get root. You can capture sensitive data from hardware devices. You can dump firmwares, of course, like in this case, this is a dump of a firmware, pretty fast. It supports, of course, Whidboard configuration of OpenOCD supports different speeds here. So in this case, the speed was limited, but we can increase or decrease depending on what are your needs. Um, Here we can see an example of the usual DUT connected over JTAG debugger port. And then we can use from one side here, just turn on the target and show you through Uart that the device is booting as usual. In the meantime, we can run OpenOCD, connect to it with Telnet, and then we can see the targets, for example. Now it's running. If you press Halt, in this case, with this specific target, you need to press it fast twice in order to block a watchdog. But anyway, as soon as you press correctly, you need to try a couple of times, of course, to get it the right timing. So now the target is halted. Yes, halted. So now we can try to dump. Here we can see even the registers, the content of each register, as you can see, is very low level access, debugging with a JTAG, debugging port interface, and then we can eventually dump the firmware and then dump with the firmware dump we can do firmware analysis. The last protocol supported by Whidboard, actually Bruschetta-Pro, which is part of Whidboard, is the SWD. You can see it as a sort of evolution or younger brother of the JTAG. It has mainly two pins or two data lines, the SW clock and the SWIO. How to interact with that? Well, you will still need the OpenOCD, and you can first using the pin enumerator feature we will see a bit in the next slides, you can use the pin enumerator to enumerate the pins, so to figure out what is SW, which pin is the SWIO and which is SW clock, and then use OpenOCD to interact with that. Here is a quick example of how we use Whidboard against the UNRF52 MCU, which has SWD interface, debugging interface enabled. And to give you an idea, an NRF52 chip is used usually in Apple AirTags, Samsung Smart Tags, IoT devices, and so on and so forth. So in this case, we use the pin enumerator feature, which is relying on the JTAG firmware. And by using the JTAG firmware on this pin enumerator feature of the Whidboard, we are able to quickly enumerate the right pins, so the SWIO and the SW clock of this NRF52 DUT device under test. After figuring out the right combination, it's just a matter of unplugging the DuPont cables on the pin enumerator and plugging them on the SWD connector of the Whidboard, and then move forward and use OpenOCD. So as we can see here in the video now, we will just do exactly that. We will, now that we know the right combination of the pin out, so we know that the SW clock and the SWIO are in the right combination, we just take them out from the pins of the pin enumerator and plug them on the right, connections on the SWD connector here. And now we can proceed further with the next video and use OpenOCD to dump the firmware. And here. So in this case, we still have the target connected to the SWD pins of the Whidboard. From one side, we use OpenOCD with -f Whidboard SWD configuration file, and then another -f with the configuration file of the target, which again is an NRF52. The target now is running, we halt it, we double check again, now it's halted, and now we can check the registers. As you can see here, we can access all the registers. We can even modify them, of course, just check OpenOCD manual to see how it looks like, modification of registers, but it's pretty trivial and easy. And then we dump the firmware. So here we dump the firmware, we dump image. As you can see, it's pretty fast. It took 20 seconds to dump it. And now we can exit OpenOCD and just double check with the hex dump the content of that binary dump. And as you can see here, we can clearly see that we managed to dump the firmware. Now, the next step will be reverse engineering it with Git, Pro, binary ninja, whatever. But from hardware hacking point of view, we reached our goal by using Whidboard from both enumeration of SWD pins and also interaction and dumping the firmware with the Bruschetta-Pro feature of Whidboard. The pin enumerator, as I said, well, it started everything because in the training I'm usually doing both in live and self-paced, I'm usually recommending JTAG as the perfect pin enumerator. Sadly, last year it became the production ended, so it became out of stock in many places and became even more and more expensive to buy it around. So for that reason, I developed also Whidboard with that pin enumerator feature in it and fully 100% compatible from software point of view with JTAG firmware in a way that all students are still, and new students will be comfortable playing with JTAG and still having something based on the same JTAG hardware available on the market, rather than looking around and spending twice the price because the original one went out of stock and is not produced anymore. To flash the firmware is pretty easy. You just need to follow on GitHub the instruction on both Windows and Linux. If you use the WidOS Live ISO, everything is pre-configured. So you just need to run the command as is shown here. And to interact with the pin enumerator feature of Whidboard is pretty easy. You just need to use screen and connect to TTY ACM0 on this with this baud rate, and you will see the menu of JTAG back again. What we can do with JTAG, well, we can enumerate JTAG, like in this case, on the right side, we were enumerating some JTAG pins, or on the left side, we were enumerating some Uart pins. You can even use JTAG as we seen in a few slides ago, enumerating the NRF 52, so enumerating the SWD pinout. So in this case, we are trying to enumerate JTAG pins. Now we are trying to enumerate the UART pins of the DUT of the target. So now we connect to ACM0 over UART. Should see the menu. First of all, you need to set up the voltage. So here you need to press V. On the right, the voltage level working, logic level voltage that is working the target. So in our case, it's 3.3 volts. Set up the channels that you want to test. In this case, I just had two wires, two data lines, 0 and 1, and then you just turn on the target and try some times, because sometimes may give false positive. So you just try again, and we'll spit out more information for sure. As you can see here, the last one obvious is TXD is 1, pin channel 1, RXD channel 0, and the baud rate is 115/200. Now you can even do the pass-through, so you can use the JTAG feature of the pin enumerator to connect directly to the UART. So now you turn off and turn on the target, you will see that you can clearly see the UART decoded, so you can even interact with it. So as you can see, I'm interacting in live through the pin enumerator feature by using the pass-through command. In this case, we will try to enumerate JTAG. So again, we connected all those possibly JTAG pinouts to the pin enumerator, 3 pins. And now we just, again, set the voltage, turn on the target, and then use the JTAG software that is pre-installed in the Whidboard to enumerate the JTAG. So here, if we press H, we see the different types of enumeration that can be done by the software. Now we set the channels that we want to enumerate, so we connect it from 0 to 3 or 4, something like that, to 3. So because JTAG has mainly 4 pins, TDI, TDO, TMS, and TCK. These are the minimum required. So now, as you can see, it's super fast. He found already the right combination of pins. Now we just need to connect those pins to the right pins here of the JTAG inside the JTAG part here of the Bruschetta-Pro, which is a feature of Whidboard. So as you can see here, we are connecting them, and that's it. We can move forward and use OpenOCD to connect to it, as I showed you before. Now what we have, we have the third main feature of Whidboard, the logic analyzer. The logic analyzer is allowing us to use 8 channels at most 24 megahertz frequency speed. We can use it to sniff different protocols, use dissectors available on PulseView to dissect different protocols. You can see here is an example of dissecting the JTAG protocol. We can even use it to dissect UART protocols. Here, a couple of examples. And it's very useful and quite nice to have in one single board. As you can see, Whidboard is a sort of Swiss Army knife for hardware hackers. So it has all the most feature that you may need at home to start hacking IoT and hardware devices or embedded devices out there. In the GitHub, you will also find a 3D printed case, which is 100% compatible and designed for that reason for the Bruschetta-Pro. And of course, you can also find always on GitHub Pizzabyte. Pizzabyte is a open hardware and free version of you can build at home with few bucks of the SensePic. So it's for those students or those guys do not have a budget, do not have a lab, do not have an employer paying for all this stuff. So you can build them quite easily by buying, this thing from AliExpress or eBay for a few bucks and then print them on GLC PCB, soldering them, and you get exactly the same feature of a SensePic with those pogo pins, but on the chip. So if you have limited budget, you can use them. You can even build yourself, if you have a 3D printer or access to a 3D printer, in some hackerspace in your city, this very nice PCB workstation that is using compatible with PC Byte and is using those 3D printed arms to to connect easily to some points or test pads on a target without soldering any cable. That's pretty much it for the presentation. As you may understand, this is just an overview of Whidboard. Soon will come out. Stay tuned. If you have questions regarding it, you can find me either on LinkedIn or on X or Twitter. Um, and have a lovely day. Stay safe and hack responsibly. Stay tuned. Take care. Bye.